All right, let's take a quick look at section 5-2. We're going to be looking at perpendicular and angle bisectors. So we have basically four, if you include the converse theorems, we're going to look at in this section. And they hinge on this vocab word, our first word for today, and that is the word equidistant. And we say a point is equidistant from two objects if it is the same distance from the objects. So it's one of those nice vocab words where the name itself kind of gives it away. It's a two-part name, equidistant, equa meaning equal or the same, distant, so the same distance. So we'll talk about what it means for a point to be equidistant from two objects as we look at our next couple theorems. Our first theorem is 5-2. It's called the perpendicular bisector theorem. And it says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And we can kind of see an example here, look in the middle portion of this theorem. And PM is a perpendicular bisector. We know that because it has two things, perpendicular, meaning it intersects at a right angle, and it's the bisector, meaning it cuts the segment in half. And we can see that by the congruent marking on AM and BM. They are both the same length. So PM is a perpendicular bisector. Now, knowing it's a perpendicular bisector, our theorem tells us any point on that perpendicular bisector, in this case we're going to look at point P, is the same distance from the endpoints. And that's what we can kind of see in this third portion of our theorem over here. They've connected PA and PM, and again, notice those congruent markings. We know that those two are congruent because of our theorem that says any point on that perpendicular bisector is equidistant from the endpoints. So PA has to be the same length as PB. Now we also have the converse of that theorem, and we hopefully remember what converse means from our beginning of our year, chapter 2 material, but that's kind of like flipping around the hypothesis and the conclusion. And it says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of a segment. So if we don't know necessarily that it's on the perpendicular, or we have a perpendicular bisector, but if we have in this case PA congruent to PM, then we could draw that perpendicular segment right through there, and P would have to be on the perpendicular bisector. So let's go ahead and practice that. We have a picture here, and we're asked to find the length of AB. And AB is kind of this left-hand side here. Well, there's a couple things we want to note. Notice right away that BD, the segment through the middle, intersects AC at a 90-degree angle, so it's perpendicular. And notice D is the midpoint of AC. In other words, AD and DC are both congruent. So that there tells us BD is a perpendicular bisector. And we can know that it's essentially given to us by looking at our picture. So using the theorem in 5-2 we just talked about, since it's a perpendicular bisector, B has to be equidistant from the endpoints AC. So BD is a perpendicular bisector of AC. So B is equidistant, that's our new vocab word, from both A and C. So I can put these little congruent markings on here. Now, looking at my given information, I know BA is equal to some expression 4x, and BC is equal to some expression 6x minus 10. And since BA is the same distance or the same length as BC, we can use substitution to solve for x. So BA, I'm going to substitute in 4x, is equal to BC, I'm going to substitute in 6x minus 10. Now I've got a two-step algebraic equation to solve. Got x's on both sides, so my first step is going to want to be to move my x's all to the same side. So I'm going to subtract 6x from both sides. 4x minus 6x is negative 2x. 6x minus 6x cancels, but don't forget about that negative or minus in front of the 10. So negative 2x equals negative 10, and divide both sides by negative 2. And negative divided by negative is positive, x equals 5. We're not done there. Always make sure that you are answering the question they ask. They don't want to know what x is, but they want to know the length of AB. So we're going to go ahead and use substitution to substitute in 5 for x. So AB is equal to 4 times x, or 4 times 5, which gives us 20. Now you always want to, when you can, double check. In this case, we can double check by making sure that if we substitute an x for BC, we get the same length. BC, it says is 6x minus 10, so 6 times 5 is 30, minus 10 is 20. So we did just verify there in less than 30 seconds that we did our algebra right. I always recommend doing that before you submit an answer. Let's try one more like that. Got a new picture here. I've got triangle PQR, and I'm looking for the length of QR. Now again, hopefully you're starting to pick these things out. Look at QS. Notice it's perpendicular and S is a midpoint. So again, I've got a perpendicular bisector. And remember, our perpendicular shorthand or our perpendicular symbol is kind of like the upside down capital T. So QS is a perpendicular bisector of PR. Therefore, Q is equidistant from both endpoints. P and R. So PQ and QR are the same length. And again, if you want, you can always add those little markings to your picture. So we're going to do that same process. We're going to go ahead and use substitution. I'm going to say 3n minus 1 is equal to 5n minus 7. Again, I've got variables on both sides, so I'll need to do some algebra to get the ends on the same side. I'm going to subtract 3n from both sides. So negative 1 is equal to 5n minus 3n is 2n minus 7. And now add 7 to both sides. Negative 1 plus 7 is 6 is equal to 2n. And divide both sides by 2 to get n by itself. And n is equal to 3. Don't stop there. We don't want to know what n is. We want to know the length of QR. So go ahead and using substitution, QR is equal to 5 times n we just said is 3 minus 7. 5 times 3 is 15 minus 7. QR is equal to 8. And again, take 30 seconds and verify that on your other side. 3 times 3 is 9. 9 minus 1 is 8. Good. We did our math right. So again, just verifying, if you have a perpendicular bisector, any point on that perpendicular bisector is equidistant from the endpoints of that sign. All right. Now the next term isn't necessarily a term, but it's a way that we talk about distance in geometry. And so we say that the distance from a point to a line is the length of the perpendicular segment from the point to the line. So really what we mean, if we look at the picture over here on the right, I've got line L, and I've got 2 points, points A and B. And we want to talk about length, or we talk about distance a lot in geometry. So we have to have a universal way of talking about the length from a point to a line. So if I wanted to say, hey, how far away is A from line L? Or how far away is that house from this road? Something like that. I need to know how I can measure that. I mean, I could take a ruler and I could line A up from A to the end point. I could do A to halfway between the end point and the other end point, or the midpoint. I could do a lot of different things, and that would give me different measurements. Well, when we talk about it in geometry, we always talk about the shortest distance. What is the shortest way I can get from A to line L? And that's going to be along the perpendicular line. And that's always going to be the case, and that's what we're going to use when we talk about the distance from a point to a line. So we can see here, we've already drawn in this segment, it's a perpendicular segment. That's going to be what we use as the distance from A to line L. Same thing over here with B, that perpendicular segment. You're not going to take a ruler and measure along a line like that. We're going to want to measure that perpendicular. It's just kind of something to keep in mind when we're talking about distance. And we'll actually see that come into play in our next set of theorems, looking at angle bisectors. So our angle bisector theorem says, if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. So very similar to what we looked at with perpendicular bisectors, just now in terms of an angle bisector. So we look at this in action in this middle portion here. I've got angle PQR, and QS is an angle bisector, and we can tell that by the angle markings down here, right by the vertex Q. Since those two angles are congruent, QS is my angle bisector. And what does that mean? Well, notice S here, that's a point on my angle bisector, it's the same distance from the top side of that angle to the bottom side. And this is why it's important to know how we talk about distance, since distance is measured along the perpendicular. So if I drew a perpendicular line from S to P, that segment would be the exact same length as the perpendicular line from S to R. And you can see that marked right here in this third picture, or third portion of my theorem. So if it's on the angle bisector, then it's equidistant from the sides. And we measure that distance along the perpendicular. Now, again, just like we did with our perpendicular bisectors, we have a converse theorem here, and it says, again, switching the hypothesis and conclusion. If a point in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector. Okay? So again, if I don't necessarily know that there's an angle bisector there, but if I do know it's equidistant, then I know it has to be on the angle bisector. So let's go ahead and try a few examples looking at angle bisectors. So I'm given a picture here. I've got angle LNQ, and I want to know the length of RM. And RM is like how we'd measure the distance from R to side LN. It's that perpendicular. So a couple things I want to notice right away. RN is an angle bisector. Notice right here I've got my congruent angle markings. That's how I can tell I have an angle bisector. So RN is an angle bisector. Therefore, using that theorem we just talked about, R is equidistant from both sides. And since we measure the distance along the perpendicular, that tells us that RM is equal to RQ. So this segment here is the same length as this segment here. And now, just like in our last couple examples, we're going to go ahead and use substitution. The length of RM is equal to 7x. And the length of RQ is equal to 2x plus 25. And solve for x. Subtract 2x from both sides. 5x is equal to 25. And divide both sides by 5. X is 5. And our last step will be to find the length of RM. We're just going to go ahead and use substitution. RM is equal to 7x. X is 5, so 7 times 5, 35. And again, that 30-second check, let's double check to make sure RP is also 35. 2 times 5 is 10. 10 plus 25 is 35. We did our math right. All right, one more example to wrap up our angle bisector and perpendicular bisector theorems. Very similar example going on here. I've got angle BCD, and again, CF is my angle bisector. So that means any point on that angle bisector is equidistant from the sides, meaning BF is equal to FD. And we'll substitute in 6x plus 3 for BF, and 4x plus 9 for FD. And solve for x. We've got x's on both, oops, I did that wrong. X is on both sides, so we want to move that 4x to the other side by subtracting it from both sides. So 6x minus 4x is 2x, plus 3 equals 9. Now subtract that 3 from both sides, and we get 2x equals 6. And our last step will be divide both sides by 2, and we get an x value of 3. And we want to know the length of FB. And FB is 6x plus 3, so we're going to substitute in 3 for x. 6 times 3 plus 3. 6 times 3 is 18. 18 plus 3 is 21. 30-second check. Let's find FD. 4 times 3 is 12. 12 plus 9 is 21. We did our math right. All right, so that's all for section 2. Just working on those two theorems. Really become familiar with recognizing perpendicular bisectors and angle bisectors. As always, if you have any questions, don't hesitate to ask, and I will be in the Math Help DI Thursday at noon. Have a great week.